Okay, so this is my video for standard 1.3, which gives us these three state vectors and asks us to perform various operations with them. So the first thing it wants us to do is find a vector that is orthogonal to psi1 and is also normalized. So let's start doing that. Okay, so let me just zoom in a little here. Okay, so we're looking for a normalized state, psi L, and I call it psi L because L is kind of like a right angle type thing that is orthogonal to psi1. So to do this, first we write down our general state vector that we're looking for, psi L, and these two coefficients a and b are just some complex number. And then we demand that the inner product of psi L and psi1 is 0. And then from there, we can just write out this inner product. And then this gives us a relationship between A star and B star. And they're A star and B star and not just A and B, because since we're taking the bra form of psi L, because we want to take the inner product with psi1, and I just chose to conjugate psi L instead of psi1. So we get this relationship between A star and B star, and then from that we can solve for A star in terms of B star, and then I just say so then any two A star and B star, any pair of complex numbers that satisfies this relationship will produce a vector that is orthogonal to psi1. So I just say, let's say B star is 1, and then that means that A star is negative I root 2. So moving on. So then we have this vector psi L, which is I root 2 times the plus basic vector plus just 1 times the minus vector. And this is orthogonal to psi 3, but it's not normalized. So to normalize, we demand that we know that psi L inner product with itself should be 1, and then we put this normalization constant out front. Now, technically what I should have done is scaled both vectors by c, and then this one is c star, but I know from doing this calculation a couple of times that no matter what, you're always going to end up with a modulus c squared out front, because when you multiply the c and c star together, you get modulus c squared. So I've just been sticking it out front here, and it doesn't really make a difference, I guess, although I guess it is technically incorrect. But anyway, moving on. So when we do out this inner product, we get 3 times the modulus of c squared should be 1. So then we know that our scaling, what we want to scale our vector by to make it unit length, should have modulus 1 over root 3. So then I just choose c to be 1 over root 3. So then this state, psi L, that equals I times the square root of 2/3 times the plus basis vector plus 1 over root 3 times the minus basis vector. We know that this is going to be orthogonal to psi1 and normalized. So they ask us to do the same thing for psi2 and psi3. And I'll show you the calculations, but I won't go very much in depth because the idea is very much the same. Here's my calculation for psi2. Again, I multiply it by the general vector, get a relationship between A and B, and then here I saw a chance, since this relationship between A and B is much simpler than the one we had for psi1, it's just A star equals 2B star, I saw a chance to maybe kind of cleverly pick B so that I'll already have a normalized vector and I won't have to normalize it. And that's what I did. I just picked 1 over root 5 and 2 over root 5, and that is like clearly unit length. I don't think there's any need to show that dotted with itself is 1. So let's go on and look at psi3, which is a little more interesting. It has a little bit of a wrinkle, but not that much. So the wrinkle here comes up here because we have a complex number written in polar form. So we use the Pythagorean theorem and the fact that it has modulus 1 to rewrite it and then multiply through by 1/√2, and then now we have it in our nice a plus bi form, and then we can just proceed as usual. So then we get our relationship between a star and b star. So here it was pretty messy, so I didn't really see a way to smartly pick my constant, so I just let b star be 1 again, and then I get this ugly thing for a star, and then complex conjugate them to get b and a. So then this is the state vector. This state vector is orthogonal to psi3, but it's not normalized yet, so let's normalize it. So we go through the same process again. Oops, I made a little typo. I wrote modulus squared around the inner product, but that's okay. Just go through the same process again, take the inner product with itself, demand that it equals 1 right here, and then solve for what our scaling constant should be, and it turns out to be 1/√2. So then this vector down here is the one that is normalized and orthogonal to psi3. So the last thing that they asked us to do is take all the possible inner products with those 3 vectors. And so I've done that calculation. Oh, that's not quite in the window. 1 second. Oops, sorry about that. There we go. Okay. So here's my psi1 with psi3 calculation. It's just straight up foiling. And then you get 2/√6 minus I√2/2√3. And then to save myself some time, so I don't actually have to do out the psi3 times psi1 inner product, we know that when we do that, we'll just get the complex conjugate of this one. So we get 1 for free every time we do this calculation. So then psi3, psi1 will be 2/√6 plus I√2/2√3. So then moving on, psi2 and psi3. Oh, I made a typo. And you can't see it. Alright, there we go. And that's psi2 and psi3. This should read psi2 right here. I don't know what I was doing. But, yep, so we get this for psi2 dotted with psi3, and then we get the complex conjugate for psi3 and psi2. So I think that about covers it. Yeah, that's it.